Hello! You may have recognized acids as a class of substances that taste sour. Vinegar tastes sour because it's dilute solution of acetic acid. Citric acid is responsible for the sour taste of lemon. Basic things like soap tend to be slippery. Bases are characterized by their slippery feel and bitter taste, but do not taste chemicals. Today we will learn these terms together. First, you need to learn about what makes an acid an acid. Mikä tekee haposta hapon? And what makes a base a base? Mikä tekee emäksestä emäksen? What does it mean for something to be acidic or basic? Mitä tarkoittaa, jos jokin on hapan tai emäksinen? What the pH scale tells us? Mitä pH-asteikko kertoo? Hydrogen ions are hydrogen atoms that have lost an electron and now have just a proton, giving them a positive electrical charge. Since H+, a hydrogen atom without its electron, is a proton, there are two ways of naming the H+ ion. Some call it a hydrogen ion. Others call it a proton. Acids are known as either hydrogen ion donors or proton donors. Bases are hydrogen ion acceptors or proton acceptors. So, acids donate hydrogen plus ions to another ion or molecule which acts as a base. A substance is said to be amphoteric if it can behave either as an acid or as a base. Water is the most common amphoteric substance. When an acid dissolves in water, a covalent bond between an electronegative atom and a hydrogen atom is broken, which gives a proton H+ and a negative ion. When dissolved in water, acids donate hydrogen plus ions to water, which acts as a base. For example, hydrogen chloride is a covalent compound and does not contain ions. However, in water, it ionizes completely to form H+ and Cl- ions. An H+ ion is transferred to a water molecule, as shown in the figure. Each H+ ion that an acid donates to water is bound to neighboring water molecules. When H+ associates with a water molecule, they form a hydronium ion. Ethanoic acid, also called acetic acid, etikkahappo, is one of the simplest and more common organic acids. When acetic acid dissolves in water, only a fraction of the dissolved molecules ionize to form acetate ions and protons. The double arrows in this equation indicate that the reaction can occur in both the forward and reverse directions and can reach chemical equilibrium, kemiallinen tasapaino. At equilibrium, the two opposing reactions go on at equal rates. If the equilibrium lies to the left, the acid is weak. Only small percentage of the acid molecules are ionized. Okay, so now we have learned that all acids contain hydrogen. When dissolved in the water, the molecules of the acid dissociate into two kinds of ions. One of these is always hydrogen cation, while the other consists of the remainder of the molecule and is the anion. The stronger the acid, the more readily it dissociates to generate H+. For example, as I showed you earlier, hydrogen chloride vetuchloride completely dissociates into hydrogen and chloride ions when it's placed in water. In this case, the water molecules win the competition for the H+ ions. Other common strong acids, vahvat hapot, are sulfuric acid, rikkihappo, and nitric acid, typpihappo. A weak acid, heikko happo, dissociates only to a very small extent in aqueous solution. As we just saw, acetic acid, etikkahappo, is a weak acid and as such does not completely dissociate in water, so the intact and dissociated forms are in equilibrium in solution. The terms strong and weak acids, vahvat ja heikot hapot, are often confused with the terms concentrated and dilute acids, väkevät ja laimeat hapot. The concentration, concentratio, tells you about how much acid is dissolved in the solution. The strength of an acid, hapon vahvuus, is determined by the extent of the dissociation of the acid into its component ions. It is possible to make a concentrated solution of a weak acid. Väkevä liuos, heikkoa happoa. It is also possible to have a dilute solution of a strong acid. Laimea liuos, vahvaa happoa. Some important acids, such as phosphoric acid, fosforihappo, can furnish many protons and are called polyprotic acids, moniarvoiset hapot. A polyprotic acid always dissociates in stepwise manner, one proton at a time. Phosphoric acid is a triprotic acid, kolmiarvoinen happo that dissociates in 3 steps. Removal of one proton gives the dihydrogen phosphate ion, and removal of second proton gives the hydrogen phosphate ion. Finally, the phosphate ion, phosphationi, is derived from phosphoric acid by the removal of all 3 protons. Sulfuric acid, rikkihappo, is a diprotic acid, kaksiarvoinen happo, an acid having 2 acidic protons. As it is a strong acid in its first dissociation step, it ionizes completely to form hydrogen sulfate ions, but in dilute solutions those hydrogen sulfate ions also dissociate, forming sulfate ions. Okay, let's talk about bases then. Bases and acids are like chemical opposites. Here you can see that ammonia is a base because it is accepting hydrogen ions from the water. Water is the acid in this reaction. Remember, water is amphoteric, so it can behave either as a base or as an acid. We saw in earlier examples how water molecule acted as a base, accepting a proton from acid. Now we see how water molecule acts as an acid, donating a proton to the base. A base is a compound that yields hydroxide ions, OH- ions, when dissolved in water. Even though the base, ammonia, contains no hydroxide ion, it still increases the concentration of hydroxide ions to yield a basic solution because it produces hydroxide ion by reaction with water. As you can see, the water molecule that lost a proton becomes a hydroxide ion. Ammonia is a weak base. The reaction shown here is reversible, and at any one time most of the ammonia is still present as ammonia molecules. The ammonium ion is conjugate acid of ammonia. It can release that hydrogen ion again to reform the ammonia. A conjugate acid is a base with a hydrogen ion added to it. As in the reverse reaction, it loses hydrogen ion. When water is acting as an acid, its conjugate base is the hydroxide ion, because in the reverse reaction, the hydroxide accepts a hydrogen ion to reform the water. Metal hydroxides consist of hydroxide anions and metallic cations. The hydroxide ion is a base, as it can accept a proton to form a water molecule. The bases sodium hydroxide, natrium hydroxide, and potassium hydroxide, gallium hydroxide, contain hydroxide ions in the solid lattice and dissociate completely when dissolved in aqueous solution. Because of their complete dissociation, the hydroxides of the alkali metals like sodium and potassium are called strong bases, in the same sense as we defined strong acids. As strong bases, alkali hydroxides are highly corrosive and are used in cleaning products. The alkaline earth hydroxides are also strong bases. For these compounds, 2 hydroxide ions are produced for every molecule dissolved in aqueous solution. Calcium hydroxide, calcium hydroxide, is often called slaked lime, sammutettu kalkki, and is widely used in industry. Acids release H+ ions in solution, and this is what makes the solution acidic. Hapot vapauttavat H+-ioneja liuokseen, ja tämä tekee liuoksesta happaman. Bases release OH- ions into solution, and this is what makes the solution basic. Emäkset vapauttavat OH- liuokseen, ja tämä tekee liuoksesta emäksisen. Large quantities of H+ and OH- cannot coexist in a solution. They react to form water molecules. Well, you remember H+ ions always associate with water molecules to form a hydronium ion. When an acid and a base react in an aqueous solution, the hydrogen ion from hydronium ion and hydroxide ion combine to form water. When H+ and OH- ions combine to form water, which is neutral, neither an acid nor a base, it brings the pH closer to neutral. When an acid and a base are brought together in solution in proper proportion, the characteristic properties of each disappear. Neutralization reaction, neutraloidumisreaktio, is when an acid and a base react to form water and a salt. If the right amount of acid is added to a base, or right amount of base is added to an acid, the solution will be neutral and have a pH equal to 7. Here in this picture, hydrogen chloride reacts with sodium hydroxide to form sodium chloride, aka table salt, ruokasuola, and water. Do you still remember that a salt is an ionic compound composed of a cation and an anion? Sodium chloride is made up of sodium cations from the base and chloride anions from the acid. Both products formed, salt and water, are neutral. Remember, in chemistry, the word salt refers to more than just table salt. The products of a reaction between an acid and a base are always water and some salt, i.e. some ionic compound. The pH scale, pH is a compact way to specify the acidity of solution. As this diagram shows, pH ranges from 0 to 40. pH values less than 7 are acidic, hypomere, while pH values greater than 7 are basic, hemaxicide. 0 is the most acidic, hypomere, and 14 the most basic, hemaxicide. Solutions are classified as acidic or basic based on their hydrogen ion concentration. Remember, there aren't really H+ ions floating around freely in water. As in water, hydrogen ions always associate with water molecules. However, we still refer to hydrogen ions at their concentration, as if they were not in hydronium form. This is just a shorthand we use by convention. As you can see from this pH scale, pure water has a pH value of 7. This value is considered neutral, neither acidic or basic. You can see that at pH 7, the concentration of hydrogen ions and hydroxide ions is equal. A basic solution contains a base that creates additional hydroxide ions, causing the concentration of hydroxide ions to increase and the concentration of hydrogen ions to decrease. A basic solution is also known as alkaline. An acidic solution contains an acid that creates additional hydrogen ions, causing hydrogen ion concentration or hydronium ion concentration to increase. Acidic solutions have a higher H+ concentration than water. In an acidic solution, the concentration of hydrogen ions will always be greater than the concentration of hydroxide ions. Since the pH scale is a logarithmic scale, a change of 1 pH unit corresponds to a 10-fold change in hydrogen ion concentration. For example, a lime with a pH 2 is 10 times more acidic than a plum with a pH 3 and 100 times more acidic than a cherry with a pH of 4. Notice that changing hydrogen ion concentration in aqueous solution produces an inverse change in the concentration of hydrogen ions, and vice versa. In all aqueous solutions, both ions are present. In an acid-base titration, happonastitrausis, a basic or acidic solution of unknown concentration is reacted with an acidic or basic solution of known concentration. The known solution is slowly added to the unknown one, while the pH is monitored with an indicator, a substance whose color depends on the pH. As the acid and base combine, they neutralize each other. A commonly used indicator for acid-base titrations is phenolphthalein, Phenolphthalein. Phenolphthalein is chosen because it will appear pink in basic solutions and clear in acidic solutions. Thus, when an acid is titrated with a base, the phenolphthalein remains colorless until after the acid is consumed and the first drop of excess base is added. Many plants contain chemicals from the anthocyanin family of compounds. Anthocyanin molecules change their color depending upon the pH. You can extract anthocyanins from red cabbage, macali, to prepare your own homemade pH indicator. Add various household chemicals like vinegar or baking soda to your indicator until it changes color. Universal indicators are mixtures of several different pH indicators. Universal indicator paper, yleisindikaattoripaperi, has many different color changes from red for strongly acidic solutions to dark purple for strongly basic solutions. In the middle, neutral pH 7 is indicated by green. You only put a small spot of the test solution on the paper and then leave the color to develop for about 30 seconds before comparing it with the color chart. pH papers or indicators have limitations on their accuracy. More accurate pH measurements are obtained with a digital pH meter. Digital pH meters require calibration. Calibration means checking an instrument to see if it's accurate. Calibration of a pH meter is done using substances with known pH levels. Most solutions will rapidly change pH upon the addition of an acid or base. However, a buffer, puskuri, resists pH change by neutralizing added acid or added base. Buffers are important in biology and medicine because nearly all physiological processes must occur within a narrow pH range. The acidity of blood is critically important and tightly regulated. pH of the blood is kept relatively constant by buffers. An important buffer system in blood is a mixture of carbonic acid and bicarbonate ion. The carbonic acid neutralizes added base. The bicarbonate ion neutralizes added acid.